Welcome back, folks. Hope you had a great weekend. Hopefully, you were able to relax a little bit, get outside, enjoy that wonderful day yesterday. I'll have week at a glance stuff for you coming out today in the email. You probably already have seen it, maybe. But today, what we're going to do for notes is we're going to talk about magnetic field from current in a straight wire. We're also going to talk about torque on a current loop as well, okay? So let's get it started. So as you can see, first thing out here is we have a little bit of a variation on the right-hand rule now, okay? So with a little variation on the right-hand rule, what you're going to see now is we just change the application of it. So instead of just using it to figure out where the magnetic force is, what we can do is we can figure out the magnetic field direction as well. So in this case, what we're going to do is we're going to use the magnetic field direction from current in a straight wire. All right. So with current in a straight wire, we're still using that thumb. That thumb still becomes super critical for us. Okay. Thumb is going to be that current or that positive charge flow, just like when we talked about the wire, just like when we talked about the proton last week. All right. Curled fingers. So now our fingers are going to wrap. That's what we're looking at. That's going to be the magnetic field. Again, our magnetic field should be circular for us, whether we're looking at the Earth, whether we're looking at, this wire. It should be pretty circular in its orientation and its direction that it's traveling. Okay. So if we look at an example here, what we have is we have wire going basically straight up towards the top. If it's going straight up towards the top, it means our thumb's going to be upwards. If our thumb is upward, that means that when we wrap that around, it's coming out of the screen on kind of the left side of me, okay, or the left side of the screen, and then it's going back into the screen on the right side. All right. It's a little trickier when we look at it upwards as opposed to kind of in or out, because in or out we can talk about clockwise versus counterclockwise. But with this one, what we're going to see is that we're basically pulling it towards us. Okay. And what ends up happening is that as we see that, the magnetic field is going to be really, really strong, close to that wire. If you remember gravity and how gravity works with us, the further away we get, the less gravitational pull we have. Same thing with this magnetic field. When we're real, real close, it's going to be pretty strong. As we get further and further away, what we just start to do is we start to use that inverse square, and we start to lose some of that strength to it. Okay. If we twist it a little bit, so instead of being up, it's over a little bit, we can see that thing's going to rotate as well around that same side. All right. If we look at a wire directed straight out of the page like we talked about, so the current is flowing directly towards our face. Boom, right towards me. Okay, and right towards you right now. All right. So if we see that, we ask, what direction will the compass needle point in this wire? All right. So if we put it there, and that compass can rotate around as much as we want it to, all right, the question becomes, which direction is this compass going to want to go? Which way is magnetic north going to be on this? All right. So if we look at this and we place our thumb in the correct spot so that our thumb is going directly out toward us, what we see is this thing should go up over the top of it, right? It should go counterclockwise, okay? So the nice thing is that we can tell that that magnetic field in this case is going to go up and around, right? Kind of counter to how that clock rotates around in our offices or in our rooms, okay? For current coming out, we get it that way. Now, what if we were to flip it? What if we were to say instead of it's going out, it's going in, all right? And again, that one's a little trickier, right? Just because as we push that thing in, we got to manipulate our wrist a little bit, which can be tough, can be a little bit dicey, right? So going into it, what we should see, this one should go clockwise, right? Should go clockwise for us, all right? And again, a nice little application of magnetic field for us, just to be able to see how this thing works off the current carrying straight wire. I mean, I suppose you could go, find a wire and see this, but it's probably going to be too far away. Okay, torque now. Torque is really one of our last big things that we want to talk about. Now, torque for us allows us to have AC motors, alternating current motors work. All right. So what ends up happening is that for us, in order to get torque, we need current flowing in a loop, so to speak. Okay. So what you're going to see is that if we put a magnetic field from the left side of the screen to the right side of the screen, and then we put a loop in there, and we have to now say, what direction is that current going to travel through that loop? So when we look at this, we see that that current up the right side is going upwards. Across the top, going left. Across the left side, it's going down. And then across the bottom, it's going to the right. Okay? Now, this one, I know it doesn't appear like it's connected to another set of wires, but what you'll see is that when we do this, we'll put a magnet on one side, a magnet on the other side, and then we'll put that loop somewhere in the middle. All right? And we'll see, we want to know, does that loop spin? Because that's the biggest deal for us, is that we want to know, can we create spin out of this thing? All right? So what we're going to do is we're going to predict what will happen in the situation in the diagram on here. So we want to know, is there any magnetic force? Again, notice we got our current going the one direction, and now we have a field line that is all kind of together. So we're going to use, whoops, sorry, wrong hand. We're going to use that right-hand rule again. Okay? Now remember, this thing is called the right-hand rule for a reason, because you have to use that right hand. All right? Looking at some of the early quiz results, that was one of the areas where I think we got some issues. And we had about 20 or 30% of our people got those questions incorrect. Again, because we have to use that, not the left hand. Okay, so we're using the right hand. All right, so let's start on the far right side. All right, where that I is. All right, so to start there, what we see is we've got I, that's going to be pointing upwards. All right, so because that's pointing upwards, what I want to do is I want to figure out what direction are my fingers going to go. Well, my fingers are going to go to the right. Okay, so then that means my palm is facing what direction? Yeah, you're right. That thing's facing in to the page, right? So that's going to cause the magnetic force on that side of the loop to go in, all right? Right across the top. Let's look at that one now, all right? Now, here's the hard part about the top. And this was one of the first homework questions we had in it, and it was probably unjust in putting that one as the first one, right? But what we see here is field's going that way. I want my thumb to go this way. Well, guess what? My thumb can't do that. So what ends up happening, because that's going parallel, or it's going the same direction, or even the opposite direction of it, there is no force in the top part of that loop, which is perfect for us. You'll find that out in a second. Okay. So across the top, there is no force. Across the right side, it's into the page. All right. So we look at the left side now. Left side, we see the arrows going down. That means my thumb has to go down. Right. Now, magnetic field still trending that way. So that means I got to have my thumb down and my hand out. So I look at this, what I see is my palm is facing outwards, right? So that means that the force on that side is going to come out towards me, out of the screen, all right? Last one is the bottom. On the bottom here, what we got is we got field that way. The current is also going that way. They're parallel, right? They're going the same direction in that case. Or like on the top one, it's directly opposite. In this case, because it's going parallel to it, it's going the same direction, there is no force. So what we should see is one's going in, one's going out, all right? So the left side, what we have is it's pushed out of the page. The right side's pushed into the page. Because the top and bottom have no force, this thing should spin. So the right side will spin into the page, the left side will come out. What we'll get is we'll get this turning effect of this thing just starting to rotate and rotate and rotate, all right? If we make it perfect, it'll just continue to spin for us. it'll just keep going for us. Okay. I got a really nice little lab for us with this concept tomorrow that I'll show you how it works, and we'll have a little bit of fun with that as well. All right. Last bit. Predict what will happen if the current is X and when the current is going in and when the current is going out. All right. So what we're going to see here is there's our B field line, right? So we want to know what's the direction of force on each wire. All right. So if the current is in for the X, let's start on the right side. Okay. So current's going in. So my thumb's going in, right? So if my thumb's going in, what direction is the magnetic field line? Well, magnetic field line's pushing to the right side. So then what I'm able to see is that thing should go down. So that X side of it should be trending downwards. Okay? If it's on the left side, if it's out, right? And now my hand goes that way, palm is up, that thing should go up. So we should see the force on these two going this direction. Okay? If the wires are physically connected in a loop, what we're going to see is this thing's going to rotate clockwise. It's going to make it so that it makes a nice little turn for us. All right? So we get something like that. Okay? Just to summarize our right-hand rules. All right, we'll use the top one the most. We'll use that particle in the magnetic field, where we'll also call it the direction of our positive current on our wire. So what we see is the thumb is our positive flow, so that's still the same. Field line, force. All right, in a straight wire, we remove the force. We just want to know where and how and what direction is that current going to cause a magnetic field to rotate. Okay, so what we see is in that straight wire, if we don't care about the force, or we don't care about the torque, or we don't care about any of that stuff, that's where our thumb comes into play. In that thumb, what we see is that's going to be the current, and then our fingers wrapping around are going to be the direction that the B field makes. Okay. Hopefully not too confusing. Adding a little bit to it. The big thing to pull from this stuff is torque and how that gets created through a loop in a magnetic field. All right. If you have questions or anything like that, send me an email. If we got issues with labs or stuff from last week, please let me know. Otherwise, if I don't see you or don't hear from you, have yourself a great day. Okay? Take care. See you, boy. See you, folks.